Dear students, so again coming to the new module that is in dynamics of machinery, that is for module name is what? The forced vibration. Okay, so now so far we studied about the free vibration and now the forced vibration. Okay, so the difference between in module 4 and module 5 is what we studied in the module 4. So that is in that types of vibration we are not going to consider what are the external forces. Okay, so free vibration is nothing but what? The vibration, the particular system of the vibration takes place without any help, that is without any external forces, okay, acting on the particular system. Okay, the vibration takes place itself is called as free vibration. But whereas in the forced vibration, so in this the all the system that is all related to this what the mechanical system, we are going to consider the external forces. Okay, because of the external forces, and there is a lot of chance of axis that is a what the there is a chance of producing a vibration. That is not only vibration, the antroidal axis, that is the centroidal axis, is not coincide with what the axis of the shaft of the machine component is called. So because of that also we are going to consider here. So because of that CG and the axis of the shaft, it does not coincide with the same shaft. Okay, so during such type of vibration also we need to consider we need to study in this chapter. Okay, so here forced vibration is nothing but what? Here forced vibration is nothing but what? The vibration that is the particular system, that is the system, the vibration takes place with the help of some external force, that is the periodic force. Okay, is called as forced vibration. Okay, so here I told you number of times here in the free vibration there is no external force. In forced vibration we are going to consider the external forces. Okay, so in module 5th, that is here we are going to study about what? The balancing of that is unbalancing of rotating masses, reciprocating masses. Okay, so and the here some 3 definition going to come. What do you mean by transmissibility and magnification factor, amplitude, displacement, harmonic force, excitation force. Okay, so different types of damped force vibration which will be acting on the particular system. So what are those 3 different types of damped free vibration, that also we need to study in this. Okay, so again the problems on this, and also one more topic is that is the critical speed. That is critical speed is also there in this model only. Okay, so the entire portion model 5th covers what this is related to that what the previous chapter, that is model 4. Okay, so now I'm going to tell you about the force vibration. I told you here take any particular system or a body or an element, okay, which is subject to a periodic external forces. Okay, so then the resulting vibration are known as force vibration. Okay, so take the any particular system, some if you apply some external force is called as what? The free force vibration. Okay, so I told you, so I will tell the later examples also. Okay, the ringing of a bell, that is a temple bell, that is a temple ring bell. Okay, so that is an best example for this forced vibration. Okay, so when an external force is acting, the body does not vibrate with its own natural frequency, but vibrate with a frequency of an applied external force. That is need to consider during the forced vibration. Okay, so here I told you now. So forced vibration is nothing but what? When a body vibrates under the influence of an external forces, then the body is said to be an under forced vibration. Okay, so best example for the forced vibration is what? A ringing of electric bell. Okay, electric bell. Okay, so if you apply a force, that is you just to ring that electrical bell, there is a sound, that is a chant, there is a vibration takes place. Okay, you are going to hear some different types of voice. Okay, that is an example for force vibration, because the bell is ringing because of what? You are going to apply you are going to press that electrical switch. Okay, then only the bell will that vibration takes place. Okay, that is an best example for this force vibration. And second one is another example is what? The vibration of an air compressor. Okay, so here in air compressor also we are going to apply some external forces, that is a motor. Okay, so that is if you switch on the motor, there is a chance of vibration takes place in the air compressor. Okay, so upcoming slide I will show diagram also. Okay, so not only the air compressor, IC engine, also electric motor, centrifugal pump, these are the best example for the forced vibration. Because so just to remember that forced vibration means the vibration takes place some external force. Okay, that is called as forced vibration, very simple. Okay, so what are the causes of force vibration in a rotating mass? Okay, so here the next question, this is also very important to mark, they may ask you. So electric motor, or you can take any turbine or any other rotating motion, that is machinery component, have some amount of unbalance left in them. Even after the rectifying their unbalance on precision balancing machines, this unbalanced rotating masses produces the centrifugal forces which act as the exciting force and causes the force vibration of the machine. Okay, so take any electrical motor, so even manufacture, because of the manufactured defects or something, okay, there is a chance of what there is a chance of unbalancing. Okay, when we are going to say the unbalance, when the CG of the particular machine or component does not lie on this axis of the shaft, then there is a chance of producing an unbalance. Because of unbalance, there is a chance of vibration. Okay, so that is about the main cause of this force vibration in rotating mass. Okay, so let me understand in deep with an equation. Okay, so consider a spring mass system. Okay, here I am going to tell, here I shown here, this is a spring mass system. Okay, this is spring, this is mass. Okay, just to apply a force downward direction, that is in periodic force. Okay, so if you apply periodic force, that omega is equal to what, the operating frequency. Let us assume the omega is operating frequency and omega n is a natural frequency. When omega is equal to omega n, there is a chance of producing a resonance. Okay, I told you in the model 4 also, resonance is nothing but one when the condition, this condition should be satisfied, that is omega is equal to omega n. Okay, so because of this, why we want to study the vibration, force vibration? Because of this, to reduce the resonance in the machine mechanical component, we need to study this force vibration. Okay, so how we are going to change this, how we are going to reduce the resonance? By changing the design, changing the speed, damping. Okay, these are the, not only this, any extra. Okay, so this is about the reduction of resonance. Okay, why we want to study the force vibration here? Because to reduce the resonance in a mechanical component, we need to study the force vibration. Okay, so again here there are two types of forces will be there. Okay, so one, that is the external periodic force, that is we are going to apply the external forces, that is external force, that is external force is called as excitation force. Okay, this term I am going to repeat, I am going to use the repeatedly while solving the problems. Okay, excitation force is nothing but what, external force, you just remember. Okay, again the external force or the excitation force again divided into two force, that is one is a harmonic force, second one is what, the non-harmonic force. Okay, for your syllabus only harmonic force will be there, harmonic force with a single degree of freedom system. Okay, while you are going to study higher, that is higher, you are going to study in higher studies, that is the MTech, that is ME or PhD level, you are going to study the non-harmonic forces in there. Okay, but for your syllabus only harmonic force will be there, that is single degree of freedom system. Okay, harmonic force, harmonic means what, the force which is in a the force going to consider what, in a wave, in a waveform. Okay, so if you use a sin omega t, then the force is called as harmonic force. Okay, what do you mean by harmonic? Suppose the road is uneven, so suppose if the vehicle is moving on a road surfaces, but the road surface is in up and down motion, up and down up and down way. Okay, so in the vehicle is moving, how that it is a moving up and down direction. Once it is going, it is the vehicle is moving in a waveform. Okay, so that is about the harmonic force. Okay, if you consider the sin omega t, if you consider sin and cos terms, that is called as a harmonic force. Okay, so here I told you. Okay, so harmonic force means what, here the vehicle is moving like this. Okay, so this is about the what, the harmonic force. Okay, force will be given in the form of sine wave or cosine wave. Okay, so here that harmonic force is denoted by F naught. Okay, so remember this, wherever I am going to use while solving the problem, F naught, that is called as external excitation force. Okay, F naught sin omega t is called as harmonic force. Okay, why we are going to consider here sin omega t? Because the vehicle is moving in a up and down direction like this. Okay, the waveform. Okay, if the waveform going to consider the force, that is called as F naught, that is external excitation force in terms of sin omega t, that is called as a harmonic force. What do you mean by harmonic force? F naught sin omega t is called as harmonic force. Okay, so this I am going to use while solving the problem. Okay, so where F naught, you don't tell that time. Okay, so again this is again if you consider spring damper system. Okay, so better understanding, so this is a spring mass damper system. Okay, this is a stiffness, this is a damper, this is a mass. Okay, so here look at, so here the F naught sin omega t, F naught sin omega t is nothing but what, the harmonic force. Okay, so harmonic force is nothing but what, F naught sin omega t. This is an, we are going to apply the external. Okay, so where F naught is equal to what, external excitation force, that is measured in Newton. F naught sin omega t is nothing but what, the harmonic external excitation harmonic force, and omega is equal to circular frequency, and t is the time in second. Okay, why we want to study, how we are going to, that is about this, the excitation force and harmonic force. Okay, now the best example for force vibration, where the vibration takes place. Okay, so let us, so consider this is a wheel. Okay, the motor vehicle wheel. Okay, four vehicle wheel. Okay, so if you take the beginning, if you the new one. Okay, so at the beginning level, the wheel is normal only. Okay, so that is the centroidal axis is at the middle. Okay, so even if you use this after 2-3 years, okay, there is a wear takes place. Okay, there is a mass, there is a wear takes place in between them, there is a mass removed from that, a very small amount of mass. Okay, if you remove while running, there is small amount of masses or tear takes place. Okay, because of this mass removed, the centroidal centroidal axis there is it going to be shifted, okay, some distance, okay, that is called as E is nothing but what, eccentricity. After some time this O can be shifted here, so because of this there is a vibration takes place, okay. Just to observe in normal vehicles also, when you are going to ride a four vehicle, if the center on this axis does not coincide with exact shaft, there is a wheel vibration takes place. Because of what? Because the mass is removed some part of the wheel, so that and centroidal axis does not coincide with this, that is shifted some distance, that is called as E is nothing but eccentricity, okay. So because of this the wheel will be vibrate, remember, okay. So here while rotating, okay, so and it is rotated in a angular frequency omega, that is circular frequency omega, okay. That force is called as f naught sin omega t, that is harmonic force, that is vibration force is not harmonic force, okay. So here the harmonic force will be there, and this one side is force will be acting this side direction, okay. So this is about unbalanced force produced in the vehicles. This is the best example for force vibration, okay. Force vibration means what? If the centroidal axis, if it is shifted sometime some distance, there is a chance of producing a vibration, that is called as unbalanced force produced in the vehicle, okay. So that is about the unbalanced force, why we want to study the unbalanced force, okay, because of this, okay. So next, forced vibration, okay. So normally vibration can be created by the following method of forcing, that is the step input forcing, harmonic forcing, periodic forcing, okay. Step here I shown, this is spring mass damper system, okay. Again spring mass system, here force is pulling down if you apply external force here, the m into s, that is called a step input forcing, that is it will take place a limited time, okay. So harmonic force is nothing but what, the force which is in the waveform, okay, that is called as an harmonic force. Periodic force is nothing but in time, okay, time to time we are going to apply the forces, okay. Periodic force, okay. So these are the best example for forced vibration, okay. So I told you like a wheel only, here it is there wheel, okay. So vibration of the floor caused by the running of heavy machinery, okay. So if you remove here, if you remove some where some mass is removed from small amount, there is a shifted of chance of axis, okay, some distance, okay. Because of that the vibration takes place, okay. Vibration of the car when the running in a uneven road surfaces, okay. So vibration is reciprocating engine due to the periodic reciprocating of piston, okay. Here also we are going to get some amount of vibration, okay, because of external forces, okay. So here so some one equation will be there, okay. So here one equation will be there, so this is also very important. So I am going, while solving the problem I am going to use the direct, okay, force vibration, okay. So consider a spring mass damper system. This is a spring mass damper system, that is a spring stiffness K. Sometimes some book they are using S, some book they are using K, okay, that is S, okay. This is a damper C and this is a mass, okay. Here we are going to apply external force F naught is equal to sin omega t. This is a harmonic force. What is harmonic force? The force which is in moving in a waveform, okay. Or consider only the free body diagram of this. So here there are three forces acting on, that is a force acting on this. One is spring force, damper force, that is harmonic force, and inertia force, okay. Given force F is equal to F naught sin omega t is acting in the downward direction here, and inertia force, always inertia force is opposite to the motion, okay. Mx double dot is the inertia forces, and damping force is also acting upward direction, that is C of x dot, and spring force S of x, okay, it is also acting upward direction. Three forces are acting upward direction, only the harmonic force is acting downward direction, okay. So here the according to the D'Alembert principle, what the summation of inertia forces is equal to external forces, okay. So mx double dot plus cx dot plus s of x, some book they are using k, no problem. S of x is equal to harmonic force F naught sin omega t, okay. The equation is solved by using the complementary function and particular function, okay. X is equal to what, cf of plus pe, okay. Centrifugal S of f is nothing but what, the complementary function, pi is nothing but what, particular integral, okay. So if you substitute all these two value, you are going to get the x value, okay. So here the complementary function is equal to what, capital X, there is a maximum displacement, that is maximum amplitude, E is equal to minus zeta omega n t sin of omega d t plus phi. This already we derived in the model 4, that is free vibration only, okay. Particular integral pi is equal to what, here this derivation is there, I am going to solve next, okay. F naught is equal to square root of k minus m omega square whole square plus the omega square, and that is whole square sin of omega t minus 5, okay. So if you substitute these values, so you are going to get the final equation, that is what is the complementary, that is what is a complete solution for this, okay. X of e minus zeta omega n t sin of omega d t plus phi 1, that is plus, where phi is nothing but what, the phase angle, you remember that, okay. So plus square root, that is f naught by square root of k or s minus m omega square whole square plus c omega whole square sin of omega t minus 5, okay. So this is about the complete solution. This equation I am going to use while solving the problem, okay. So in actual practice the value of a given complementary function is also too small and which is neglected. So just you take the amplitude A is equal to f naught whole divided by square root of k or s minus m omega square whole square plus the omega whole square. Okay, so this is about the just basic force vibration equation. So in the later class I am going to repeat, I am going to derive some more equations, some more derivations. Okay, so this is about what the introduction to force vibration. In this class you are going to remember the force vibration is nothing but what, here the unbalance takes place because the axis of the shaft will be shifted. That is first case. Second case is what, the external forces acting on that. And third case is harmonic force. Okay, harmonic force is an external harmonic force that is also called as an excitation force, which is equal to f naught sin omega t. Okay, these three equations you have to remember in this class. Okay, I hope you understand why we want to study the force vibration, because of to reduce the resonance in a mechanical component. Okay, so these are the some important points to be remember in this. Okay, so I hope you understand this force vibration, just basic introduction. Thank you.